Hi there, folks. Today we're looking at exponential growth, and exponential growth is basically an exponential function, so it's the same exponential functions that we've been dealing with so far, but it's special in that it's the version of the exponential function in which y is increasing as x increases. All right, and so when we talk about x increasing, that really, from the perspective of a graph, is just when the graph goes from left to right. So x increasing as we go left to right, y increases, so the graph goes up, okay? And so if we think about it that way, as we look left to the right, the graph goes up, the values are getting bigger, all right? And this happens specifically, we can make a little note here, when the b value is greater than 1. So when we have a b value that's bigger than 1, that's when this is going to happen, all right? For example, if I look at something like this guy, if we kind of think back to the patterns that we found in terms of exponential functions, for exponential functions, this a value kind of acted like the y-intercept, that was 0, 2 then. And then this b value kind of acts like what we multiply by, so times 3/2, so times 1.5. And so if I translate that over here onto the graph, I start at 0, 2, and now I multiply by 1.5, so times 1.5. So I'm right now at a y value of 2. If I take the 2 times a 1.5 times 1.5, and you can use your calculator if you need to, gives me a 3. So that's my next y value, all right? And so I just keep going over. If I go over another one, well, I'm going to multiply by 1.5 again. But see, now I'm from a height of 3. If I do 3 times 1.5, it gives me 4.5. That's my next y value. And if I take the 4.5 times 1.5, it gives me 6.75. That's my next y value. Let's see, 6.75 up here. And then if I did 6.75 times 1.5, that gives me a 10.125. That's going to be my next y value, all right? And so that's the pattern we discovered as we looked at these graphs. We want to use that to our advantage so we can graph this thing very quickly, all right? Going back the other way, we would have to do the opposite. We would have to divide, so it would come down to like 1.33 if I divided by 1.5 on my calculator, and then 0.88. And I could keep going, all right? But now from here, I mean, we just know that this thing is going to get closer and closer to the x-axis, okay? And so that's what this thing looks like. And as we look at this thing, we can see that the values are going up as I go from left to right. They're increasing. That's what exponential growth is. It's an exponential function that goes up, that increases, that gets bigger, okay? And we can see the b value this time was greater than 1, being a 1.5, okay? If I look at this next one, the next one, you might look at this and say, well, that's not exponential growth because the b value is a 1/2. It's not bigger than 1. But be careful. Look at what's written here. You see this exponent is actually a negative x, all right? And so this isn't written in the proper format for y equals a times b to the x right now, all right? I would have to make that x a positive. And so remember what negative exponents do. Negative exponents flip the fraction. And so if I use that negative exponent, it flips this fraction so that 1/2 becomes a 2. And now I can rewrite that as a positive exponent. All right. And really, this doesn't happen a lot with exponential growth. But with exponential decay, the next thing we're going to look at, a lot of times instead of writing a fraction, we'll use a negative exponent. There are certain formats where a negative exponent is more appropriate than writing a fraction. And so sometimes we'll express exponential decay using negative exponents. So I just want to make you aware of that. Watch out for those negative exponents, because what we think we see as the b value in reality might not be that b value. We might have to apply that negative exponent first in order to find b. And so now if I use the patterns we discovered earlier, this is the y-intercept, so that's 0, 3. And then the b value right here, that's what I multiply by. So I'm going to multiply by 2. So I start at 0, 3. And I multiply by 2. Right now I'm at a height of 3. Times 2 is a 6. That's my next y value. And now if I go from the 6, times 2 is a 12. That's my next y value. And that's kind of off the graph. It's way up here somewhere, okay? A little higher than that probably, all right? But now if I go the other way, well, I just start dividing by 2. So I cut this in half. And I cut it in half again. And the reason I do that is because as I go left to right, I want to be doubling this thing. So right here, here's my times 2. See, times 2 to get me to this, and then times 2 to get me to this. From here to here, it's times 2. I'm doubling the height. All right? That's how we want to use that b value in terms of the graph. And of course, we get closer and closer to the x-axis. Oh, without touching, I missed all those points. Let me try again. Okay, so that's exponential growth. It's increasing, it's getting bigger. Okay? If we look at these, we want to determine what kind of function and equation this is going to have. And so if I look at something like this guy, again, to determine if it's exponential, we just look to see if we're multiplying by the same thing each time. And so for this one right here, it's times 2, and then times 2 again, and then times 2 again, and then times 2 again. So I'm multiplying by 2 each time. So this one is exponential. And I can tell that it's exponential growth just because of the b value. Remember, these guys right here, what I'm multiplying by, that's the b value. So this one is exponential growth. And I can tell it's exponential growth for 2 reasons. One, because the b value is greater than 1. But look at the y values. They're going up. They're increasing. They're getting bigger as I go. So this one is exponential because I'm multiplying by the same thing each time. And it's exponential growth because it's increasing, because the b value is bigger than 1. Okay? If I look at this guy, I can see that it's increasing. So we're thinking along the lines of growth. This thing is growing. But the question is it growing exponentially? And so I look at this and I say, okay, to get from here to here, I have to multiply by 1.5. And if you're having trouble determining that, well, think of it this way. What I'm trying to find is 4 times something equals 6, right? That's what I'm trying to figure out. 4 times what gives me the next value. Well, think about it like an equation. Solve for question mark. Divide each side by 4. 6 divided by 4, okay, is a 3 over 2, is a 1.5, okay? And then check the next one. Say, okay, 6 times what will give me an 8? And if you need to come back up here and solve it again and say, hey, you know what? 6 times something gives me an 8. Is it a 1.5? Well, divide each side. Divide each side by that 6, and you get 8 over 6, which is 4 over 3, which is 1.3, repeating, okay? And then to get from 8 to 10, well, now I would multiply. That's completely different. It's let's see, times a point. Sorry, I divided it backwards. 1.25. So times 1.25. So if this is increasing, it's not increasing exponentially, and it's not increasing exponentially because I'm not multiplying by the same thing each time. And here's the thing, you're looking at this probably going, well, the pattern is obvious, Mr. Jansen, all right? I was just checking exponential. Well, the pattern here hopefully is obvious to you. The pattern is we're adding 2 each time. And so the idea here is, yeah, this is increasing, but it's increasing because this is a linear function with a positive slope, okay? And so it didn't ask me yes or no, is this exponential? It just said identified. This is a linear function. And it's linear with a positive slope. This one has a slope of 2. That's why it's increasing. If I look at the next one, again, same kind of thing. I'm looking at it going, okay, maybe you look for addition this time first, okay? And it's not happening. We see that it's increasing, but what kind of function is it modeling as it increases? Is it exponential? Is it linear, okay? And so as I look at this guy, I can tell that I'm not adding the same thing each time. So then I go back to the idea of, well, let's divide. Let's work our way backwards and say, okay, 16 times what gives me the 40? Well, just do 40 divided by 16. Gives you a 2.5. So times 2.5, and we can check that on our calculators if you need to. 16 times 2.5, yeah, it gives me the 40. And then ask the same question again. Say 40 times what gives me the 100? Well, let's do the 100 divided by 40. And once again, it gives me a 2.5, so times 2.5. And then keep checking. And maybe from here, you just assume that we think it's 2.5. So do 100 times 2.5, and it does give you the 250. And then do the 250 times 2.5, and it does give you the 625. And so we find out that, yes, this thing is increasing. It's getting bigger. The b value is 2.5. This is exponential. So yeah, I'm going to say that this is exponential growth. Okay? So again, not only we're determining, is it exponential? Are we multiplying by the same thing each time? But now we're adding in there, what kind of exponential function is it? Is it growth? Is it increasing? If I look at this is exponential growth, the model for standard form. This is standard form of an exponential growth model. And this is still y equals a times b to the x, okay? But we've changed it a little bit. I've changed the variables a little bit. Instead of x, I now have time. I have t in there, all right? And instead of b, I have 1 plus r, all right? And a lot of times when we talk about exponential growth from a real-world perspective, we talk about it increasing by a certain percent, okay? And so a percent increase gives us a value that's greater than 1. If you think back to like questions where we were asked to find certain percentages, like finding tax, okay? Tax is a 6% increase on top of the price. And so when we calculated sales tax, we would do 100. We would start with 100% of the cost plus 6%. So it would actually be 106%. And so we'd write it as 1.06. The same thing is happening here. If I gave us a rate of increase as 6%, we would in here do 1 plus 0.06. I didn't write the 0. Let me try again. 0.06. And I would come up with 1.06. Okay? That's the idea here. When you think about increasing by a percentage, you take that percentage and add it to 100%. But when we plug things into these equations, it's always decimals, okay? So the growth rate is what we're talking about now. That's the percent of increase, all right? This is the percent increase, but always as a decimal, okay? So when we think about the growth rate, it's how much this thing is increasing. How much is it going up by in terms of a percent? But we write that as a decimal when we plug it into the equation. And again, that's why in the equation, it's 1 plus that percent. That's how we calculate the increase. We say, hey, we do 1.0 something times that guy. Well, that increase amount, that thing we're multiplying by when we find percentages, that's what goes in for my b value here. Okay, and that's kind of what this equation does. It kind of has all that work built into it, so we don't have to think about it as much. Okay, and then t is the time. So a is still the initial amount. It's like the y-intercept. It's where we start. Okay, so the a is the initial amount. R is the growth rate. Again, that's a percentage of increase, and t is the time. For example, if I look at something like this, it says you deposit $500 in an account that pays 8% annual interest compounded yearly. Okay, and compounded means that's when you're going to increase. So you're going to increase 8% each year. So each year you get an extra 8%. Okay, and we want to know what's the account balance after 6 years. All right, and the idea behind a compound, if you've ever heard of simple interest versus compound interest, simple interest is when you only get interest on the initial 500. But compound interest is when you get interest on the 500. And now once you have that increase, now you earn interest on the new amount, including what you've already accumulated, okay? So it's basically like cumulative is what we're talking about when we talk about compound interest, okay? And so as we look at this from the perspective of this equation, it's y equals a times 1 plus r raised to the t. And so this time, the initial amount, what we start with is 500. Okay, that would be like my y-intercept on the graph. The percent increase, the rate here is 8%, but remember, we're going to write that as a decimal, so that's 0.08. And then the time is t is 6 years. And the other thing we have to be careful of here, we have to make sure the units match. When we look at something like this guy, it's annual interest, compounded yearly, which is per year, so that matches the annual, and the time is in 6 years. If any one of those things don't match, we have to change the value so they do match. All right? If it was compounded monthly and it was a monthly rate, we would have to change the years to months. Okay? And so make sure the units match. And so that's it right here. As we simplify this, and I'm going to simplify it, I'm going to do one step here before I plug it into the calculator. That's 1.08. Okay, and keep in mind, if I wanted to increase the value of something by 8%, I would say, hey, 100% plus 8% is 108%. I would multiply by 1.08. That's my b value. The b value is the thing I'm multiplying by. Okay, and so if I want to increase by 8%, that's what it looks like. And hopefully you can see that here. You can see the a, you can see the b, and you can think back to how we did percent problems originally. Well, that 1.08, that's what we would multiply by if we were finding an 8% increase. So now this is a job for my calculator. When you plug it into the calculator, make sure you do the 1.08 raised to the 6th power first. And it gives me some ridiculous decimal and then times the 500, okay? Or when you plug it into the calculator, make sure that you plug this in exactly the way it's written and you use the parentheses exactly the way they're written. And when you do that, it looks like it gives me $793.44. Always round to 2 decimals when we're talking about money, okay? And you might look at that and go, okay, so I went from $500 in the account to $793 in the account. I mean, I only made $293, but think about what you did to make that money. And the answer is nothing. You literally had to just not spend that money in order to make almost $300, okay? Interest is a great deal. Even if it doesn't give you a lot of money, it's giving you that for doing nothing, okay? If we look at this guy, it says you invest $500 in an account that pays 12% APR compounded monthly. How much will the account have in 2 years? And so right here, there's a lot of issues in terms of the units. If you're not familiar with this term APR, APR is annual percentage rate. So it's basically saying 12% per year, compounded monthly. How much is it going to be in 2 years? And so the units are all over the place here. All right. So as I start to think about this, let's make all the units match. 12%, and that's per year. The compounded is monthly. And as a general rule, it's always easiest to go to the smallest unit of measurement. And so here we have years and we have months. The smaller unit is months. Okay. So right here, 12% per year, let's convert that to per month. Okay, if it's 12% for the year, what is it per month? What is it for each month? And hopefully you can look at that and go, well, all I have to do is divide by the number of months, right? So divided by 12, so that would be 1% per month. And so I convert this, I make it months so that the units match. And so when I look at this thing, as I go to plug this in, I say, okay, y equals a times 1 plus r raised to the t. Right here, the initial amount is 5,000. The rate is going to be 0.01. Remember, I do that percent as a decimal. The time, then, instead of 2 years, that also has to be in months. So that's going to be 24 months. So again, it's really important that we make the units match. Okay? And now as I simplify this, let me show one step by hand. And again, the reason I like to show that step by hand is now we can see this thing in y equals a times b to the x format. When we think about the percent, if I want a 1% increase, I multiply by 101%, 1.01. That's the b value. That's the thing I'm multiplying by. And so as I plug this into the calculator, again, make sure you do the exponent first, and then multiply by the 5,000, okay? So it looks like for this one I get $6,348.67, okay? And again, money round to 2 decimal places. So exponential growth is when it's increasing, the b value is greater than 1. In the this model that we're looking at, the standard model, we want to show that as a percent increase. We want to add that percentage to the 1, okay? The next piece of this thing is looking at the natural number e. We call it the natural number. Sometimes it's called Euler's number. But this e represents a number, and just like pi, you know, pi is actually a Greek letter, but when we think about pi, we think about it as a number. We're going to treat e kind of the same way. All right. The value of e is found using this expression as n approaches infinity, and that's not really important for our purposes here in Algebra 2. You can talk with your pre-calc and calculus teachers about that in the future when you start talking about limits and that kind of thing. But really, the gist of it is this. We just need to understand that e is this approximate, never-ending, never-repeating decimal right here. All right, this is the value of E, and we call it the natural number. Well, it does actually appear naturally in certain situations, and for our purposes today, we're going to be looking at it from the perspective of exponential growth, okay? And so this naturally appears in exponential growth examples when we have what we call continuous growth. And so what we'll be doing here is we'll actually be using E as part of our calculations. And again, this is the approximation for E, and a lot of times when students plug this in, just like pi, we sometimes estimate as 3.14. E, a lot of times, we'll estimate as 2.718. All right, is usually the values that we use to estimate it, okay? Just like pi, we use a certain number of values to estimate it, 3.14. With E, we typically use 2.718, all right? And just like pi, our calculator actually has an E button on it. All right, and so for our purposes, we don't want to use the rounded off values. We'll actually use the E button on the calculator. Likewise, when you do pi, you should just use the pi button on your calculator at this point. It's a little bit more accurate. It gives us a few more decimals at times, okay? For example, when I look at something like this guy, again, I just go over to my calculator and pull up two of my calculators here. But on these calculators, E can usually be found as one of the secondary buttons. So when you hit like these shift keys or the second keys that are kind of located here, it gives us a new set of buttons. And it's always the things that are written above the buttons. If you locate the button that has an LN on it, down here on the TI graphing calculator, you see the LN, and then in yellow, you see an E to the X. It's probably hard to see on my screen, but if you have one of those calculators, that's your E raised to the power button. Likewise, on the Casio, there's the LN button. It's kind of right in the middle of this thing, and notice in yellow, you have that E to the X. So if I wanted to do E to the second power, on this calculator, I literally hit that E raised to a power button, so it's the shift key and then that LN button, and it uses that value above. And now raised to the second power. Notice, my calculator literally uses the value of E. Well, it's using the value of E rounded to a certain number of decimal places, okay? And so I plug this in, I get a 7.39. So I'm just going to round it to a few decimal places there, okay? If I look at the next one, same kind of thing. I'll use my Casio graphing calculator this time. But again, I hit the second key and then that LN button. That's how I use those secondary values. And I want to raise it to a pi. I'm going to use the pi button on the calculator as well. So there's E raised to the pi, and I hit enter, and I get 23.14. And regardless of the type of calculator you have, any kind of scientific calculators will have this on it. The little TI-30s will have it as well. Again, it's located as part of that LN button. You have to hit the second key and then the LN button typically. And then this last one, again, I'm going to use just my Casio because I prefer that one. But here it is, E raised to the 0.5 power, and I get 1.65. Okay, so again, just like we use pi when we're dealing with circles, and we have this basic understanding of the value of pi, now hopefully we have a basic understanding of the value of E. We're going to use this in the context of exponential growth and then later exponential decay. And so here's where this thing comes up, continuous exponential growth models, okay? So continuous exponential growth, it's A of t, the amount based on time. That's function notation like f of x. So the amount based on time, or you could even call it y equals, it doesn't matter, okay, equals a times e to the kt, where a is still the initial amount, just like it was in our standard model, all right? K now is the growth rate constant. Instead of just being a regular old rate, it's not typically expressed as a percentage. We just express it as a constant value associated with the growth, all right? T is still the time. But now we have E kind of thrown in here. It's A times E to the KT. And so notice E is not defined down here. That's because that's the natural number E, all right? And so when we look at this continuous growth, will either be indicated by something being compounded continuously, all right, when we look at kind of those financial examples, or when the increases in terms of growth are not set to an exact schedule, they're always happening, okay? If growth is always taking place, then we would consider it continuous growth. And so this is used for a lot of like population type of examples and biological examples because we don't have control over those things in terms of, hey, the growth is going to happen once a month or the growth is going to happen once per day. growth is continuously happening kind of on its own schedule, all right? And that would be considered continuous growth, all right? And so when we look at something like this guy, here it is. A colony of bacteria has a growth rate constant of a 0.045 per day. If the colony starts with 100 bacteria cells, how many are there after 5 days? And again, this is a continuous growth model because we don't have this set to a schedule, all right? We can't say that, well, the bacteria are only going to increase in size like once every hour or once every month or once every day, all right? They're continuously multiplying and increasing in population, okay? It's not set to an exact schedule. It's always happening. It's always in flux, okay? And so when we look at this, that is the indication that it's exponential growth in terms of our continuous model. So A times e to the kt. And now, once again, I just plug away the same way I normally would. I would say that, hey, A, the initial amount is 100, times e to the k. The k value this time is the 0.045 times t, which is the days. And again, make sure the units match. The growth rate constant was per day. My time has to be in days. And over here, this is the amount based on 5 days. Again, that's function notation. That's really the same thing as saying y, saying the amount after 5 days equals this. Well, again, this ends up being just a job for my calculator. So the amount here, again, if I pull my calculator up, 100 times e, and then put this in parentheses to make sure that that whole thing becomes the exponent 0.045 times the 5, okay? Parentheses, order of operations become really important here. So again, 125.23, I'm just going to round it to 125 because I'm just going to round to the nearest bacteria cell, okay? Think about the context in which we're asking this question, okay? But that's it. All right, we're doing the same things. We're plugging them in kind of the same way. There's the same types of values, but because it's continuous growth, I have a slightly different equation that's based on the natural number, okay?